Good morning. This is CFRG session. Um, Today I'm the only chair, so I'm being slightly disorganized, and my slides haven't uploaded into the online deck. So I'm just trying to figure out. So just give me 2 minutes, and then we'll get started. Hmm? Well, yeah, I just uploaded it like an hour ago, so they're not there. What?
That one, yeah. Then manage slides. And you should be able
Oh,
to, should be an update.
this.
Yeah,
Yes. Hmm. Import this deck.
yeah. I think there's a
Right.
button to import them all.
Oh, actually, hold on. It's already did it, but I haven't refreshed. Fine. All right.
Hit the refresh button.
Fine. Okay. How do I close it now? Ah, here. Okay. Close. Refresh. All right. Excellent. Thank you. All right. Good morning again. Welcome to London and to the CFRG session. Um, I'm one of your three co-chairs, the only one present in London this time. So let's get started. I think we have a note taker. Thank you, Ross. Um, and oh, what do I do? Right. Okay. Yes. My apologies. Your chair is being very confused about. Ah, here we are. Fine. Okay, so we have minutes being taken in the notes on the notes page. If this is your first IETF, then please make sure that you know the note well and various documents relating to intellectual property and proper behavior, code of conduct. Um, and just a reminder, so this is our IRTF session where we conduct research. We don't really do standards. Sometimes they get, CFRG is a bit unusual because they get used by IETF quite a bit, but CFRG can do some more experimental stuff and work on documents that are not necessarily applicable to IETF right away. So this is our agenda. You can see it's quite light. So we asked for 2 hours, but we have about 1 hour. Any agenda bashing? Okay, assuming none. This is the status of various documents in CFRG. My apologies for the small fonts. We actually have quite a bit of documents in flight and in active development. CFRG #2 curved is now in RFC editor's queue. VRF document is pending ISG review. We are not waiting for IRTF chair for anything at the moment. We have several documents in research group last call. We have Ristretto. The second last call is because the first one in June had no feedback. Luckily, we're getting more reviews and more comments this time, but if you are planning to review this document and haven't yet, please do this as quickly as possible. And as it happened, this is an older version of my slides. So we actually have a couple of more documents in last call. RSA blind signature is also in last call. And VOPRF in research group last call. We have several documents recently adopted after the last IETF meeting. Yeah, so we have 3 documents. Deterministic signatures with noise had a somewhat interesting history, so we had to do second last call to ask about third-party IPR. But this is finally adopted, and we have also IEGS family authentication encryption algorithm and BBS signatures. Any comments, questions on these couple of slides? All right, with this, I think we can start our various presentations. And the first one is being Tobias Looker on BBS signatures. Tobias, I can see you. I'm not seeing your slides yet.
Yeah, so are you going to share from your end, or would you like me to share?
I can drive them if you like.
Thanks. Looks like there's a deck. Oh, perfect. Yep. Next slide. Cool. So this is just a bit of an update and a recap. So BBS signatures as presented in IETF115 is a multi-message digital signature supporting zero knowledge proofs, proof of knowledge of the signature, and selective disclosure of the signed message set. Just checking that you can hear me all right. Sorry, Alexa, are you able to hear me okay?
Yes. Yes. Sorry.
Okay, thanks. So a bit of a recap on some of the core properties in a little bit more detail. The signer can sign a set of multiple messages and a header producing a fixed or constant sized output signature. Approver in possession of a signature and the set of messages and header signed can then generate a randomized proof over them. And the verifier can then validate the integrity of the messages and that the prover is in possession of the signature without revealing it. And the header is a compulsory payload that has to be revealed in any derived proofs. Next slide, please. So as said, validating the proof means that the prover who generated the proof is in possession of the secret signature that remains unrevealed that was used to sign the original set of disclosed messages. No other information is revealed in the proof. So the proofs are said to be unlinkable because the signature, which is fixed as issued, is unrevealed. Next slide, please. This is just a quick recap on some of the performance metrics that we shared at last IETF 1114 meeting. The benchmarks of the various operations running on a Spec MacBook Pro is revealed there with a 50% disclosure rate of the messages and the generated proofs. Next slide, please. So just a bit of a status update since IETF 1114, the draft's been adopted. So we're now formally adopted as a work item. There have been multiple reference implementations of the specification since then. I think we have 3 or 4 interoperable implementations with the current published draft. There's also some new academic work going in looking at the security properties and potentially offering some efficiencies that we're keeping an eye on. Next slide, please. A further status update is last time when we presented the work originally in IETF 1114, we had the concept of cipher suites in the spec, but we only had one cipher suite defined. However, through working group meetings subsequently, we've decided to implement a second cipher suite that uses an alternative digest algorithm, still based on the BLS 12381 curve. So we now have 2 cipher suites, one using SHA-256 and the other using SHA-256. Next slide. Yeah, so as I actually just spoke ahead of the slide, the reason for doing so is because of the predominance of the hash-to-curve implementations, specifically over the BLS 12381 curve. We found that there was significant implementation convenience in offering a SHA-256 based cipher suite, similar to how BLS Signatures offers that. However, the SHA-256 cipher suite has also been retained. In the status update as well on the signature test vectors, we have updated these in the specification to promote interoperable implementations. We've added in fixtures for mapping messages to scalar values, which is a prerequisite operation to a sign or verify operation. We've also have a set of proof fixtures, but we haven't formally added them into the specification yet. Next slide. The reason for that is we're still sort of reviewing some proposals around the proof fixtures because the proofs by nature are randomized, which is it can be a challenge for interoperability testing, having to seed RNG or the likes. So we're still considering different strategies that might improve this. And lastly, one of the issues we've been considering quite closely is how we use the expand message function in hash-to-curve, which is for us at the moment creating an upper limit on the number of messages that we're able to sign. We're currently limited at 1,365 messages, but we have a couple of different solutions that we are working through that have different trade-offs associated to them. And just to call out to thank Riyadh, who offered some advice on the solution, possible solutions to this problem. Next slide. So the next steps from here is we can continue to work with some of the new academic work that we see emerging around the scheme, and use that to take advantage of any further performance or security improvements, add in some proof test vectors, apply some suggested updates that are pending from implementers of the scheme, and further refine some of the editorial notes in the scheme and request wider review. And that's it. Thanks.
Any quick comments, questions? Go, Richard.
Hey Tobias, thanks for this work. I just wanted to speak up in support. Like I've been commenting on the JWP BOF that was done over in the Jose space. I found this draft really critical to understanding the general shape of BBS, because despite the use of signature in the name, it really is quite a different primitive than your generic signature primitive, and especially when it comes to kind of how it gets used in practice. So I think this is a really handy draft to have around. Look forward to future work on this. Just one quick question for you, Tobias. You mentioned other curves, other kind of suites to go with this. Can you comment on kind of post-quantum security and whether there are post-quantum options for this protocol?
Yeah, so thanks, Richard. So the construction, the Cipher Suite abstraction layer requires two kind of key properties as inputs. One is a digest algorithm, and another is an appropriate curve. The curves themselves have to be what is said to be peering friendly in nature, to a specific type of peering as well. So given that many post-quantum primitives, and even based on elliptic curves, mapping conceptually to the concept of peerings is quite different. So we continue to sort of look generally around the kind of equivalence and properties, but personally haven't encountered equivalence yet.
Okay, thanks.
Okay, Michael.
Yeah, Michael Peruk here. Thanks, Tobias, for this work. This is excellent. Following it closely, obviously, though probably not commenting as much as I should or would like to. Just a question on leanings around the expansion problem. I understand, like with option one, you're calling out some additional complexity. However, that kind of is my read correct that gives us more or less an unbounded space if we need to assign an indefinite number of messages for some reason?
And that we're proposing is 2 to the 48, effectively,
okay.
Number of messages. So still finite, but you know, effectively for most implementations,
Yeah,
we expect it to be a pretty reasonable upper bound.
Cool. Have you looked at all? I know like Lobachevsky and some of the other stuff going on around lattices and zero knowledge, selective disclosure type properties. Have you evaluated any of that stuff at all? From, I know the question came up on post quantum, obviously, and there are some interesting developments that are obviously still way too early for any practical implementations yet. But is that the kind of thing you possibly see as a, you know, comparative type of approach as opposed to a pairing approach, but would have similar structures as far as schemes and, you know, providing a mechanism for like multiple keys and multiple parties the way we see with BBS?
Yeah, certainly an active area of interest. We haven't formally looked at the work, but I'm very keen to sort of follow along with the developments and look for equivalent properties as those new primitives and approaches emerge.
Okay, perfect. Thanks so much.
All right, thank you, Tobias. Well, all right, so next is Andrei Boshko is going to talk about classification of IED properties. I think we had a presentation last year talking about some early discussions, and people keep bringing AEDs to CFRG. So I just thought that it would be good to have some starting discussion to try to kind of rationalize and maybe inspire some discussion. So where we want to go with this. So.
Yeah, sure.
Hold on.
Good morning, everyone. My name is Andrei Boshko, and today I'm going to talk about draft-on properties of AED algorithms. Next slide, please. AED has always been a hot topic for discussion in the CFRG, and the motivation for most of this discussion is the fact that we want to have some algorithm or algorithms standardized for the few use. However, it was noticed in one of the most detailed discussion on the topic, some citations from which you can see on the slide, that it isn't exactly clear by which criteria to choose. Because there are a lot of properties, use cases, and some of these properties may contradict each other, so there is a problem. In fact, with the AED field getting really intense, it seems like the level of understanding and structure is decreasing. I felt motivated by this discussion. I decided to contribute to a problem a little by approaching properties of AED algorithms. Next slide, please. And actually, there are a lot of them. Like on the slide, you can see a fraction of these properties. And the problem with them is that different researchers may use different language, different terms, different ways of defining these properties, and they even may use different names for the same property. Surely that leads to a lot of misunderstanding between everyone, between protocol designers, between algorithm designers, between implementers. So it seems like we need more structure. Next slide, please. The main idea is to collect all known properties to something like at least properties vocabulary, where for each property there would be a definition, a synonym, some example of some algorithm examples, few reading notes, and one of the most important functional applications, or how that property can contribute to the higher level protocols and applications. However, it was noticed in the discussion with Chris Wood that such vocabulary won't actually be useful for one of the groups for protocol designers. So the question is how to make it useful for them too. Next slide, please. And the current idea is to provide something like a reverse mapping from functional applications, functional requirements to the properties which are implied by them. Well, for example, if a protocol designer knows that his protocol is to be used on virtual machines, the randomness can be repeated. So he opens the charts, looks for that application, and understands he needs noise misuse resistance, just like for example. Next slide, please. Yes. What is done at the moment in the version 0.1, I have covered something like around 20 properties for which of them the first version high-level definitions were given, some synonyms, a few readings. The first version is like a proof of concept, like a starting point for the discussion of a problem. Next slide, please. In the next version, I'm going to address new ideas and issues which emerged in the discussion with Christopher Wood. First of them is to solve the issue with the interfaces of AAT. It is a really interesting issue because some properties imply non-standard interfaces, and it is not really easy to tackle. The next one is to improve the classification, because I feel like at this moment it isn't really good. And the most important points are to add first functional applications and add new properties. Next slide, please. Finally, I have several questions, like call for help for the CFRG. First of all, do we need such document? Do you find it to be helpful? Will it contribute to the cause? And secondly, I would really like to hear if you find some properties which are necessary to be covered and applications. I will be really glad to hear from you on the matter. Well, that's all. I am also will be very happy to answer your questions.
Jonathan Hoyland, Cloudflare. Have we given any thought to the fact that the literature doesn't agree on the definitions of these terms? So we'll have to be making a decision on what the literature means.
Yes, it is a really huge issue. I don't have like a approach for all the made-up approach. However, I think it is why we need to discuss these properties. This is why we have to understand for which properties it is the issue, and I'll discuss which definition we find more useful, more easy to understand, and more like applicable for higher-level protocols.
Thank you.
Sorry, just a quick reminder. Even if you're local in the, attending physically, please try to join the queue through the app, saying, so that I can manage the queue. Paul?
Yeah, Paul Wouters. With my security AD hat on, I would want to answer your first question, which is yes, I would definitely like to see this document.
Thank you.
All right. All right. I think at this point, we're not asking about adoption. This is very early on. This is more for people to be aware that there is a draft and have a read, comment, contribute, and then we'll discuss probably, and the following CFRG or.
Yes, sure. That's right.
So thank you for this. Thank you.
Thank you very much.
One small comment. I would
sorry.
like Andrei to send a message to the list to attract some attention to the draft, and then after some possible discussion in the list, it may be possible to ask the chairs for an adoption call after some preliminary discussion takes place.
Okay, thanks. Really glad to know it.
All right. Thank you. Okay. Yeah, I think you stand there.
Okay, may I start?
Yeah. And I'm happy to draft slides.
Thank you very much. My name is Yuto Nakano, and I'd like.
Speak up a bit.
Okay.
It is working, is it?
I think so. Okay, thank you. So my name is Yu Tanakana, and I'd like to present the encryption algorithm called RockIS. Draft is available as shown in this slide. So could you go to the next slide, please? So the background is that the internet speed is increasing and some new services has been considered, such as holography or digital twin. And some of these new services require much more higher data rate. And for example, 100 gigabps are required. And in order to realize these services very securely, a high security encryption algorithm with very high speed performance is required. And RockIS is the new encryption algorithm that satisfies these two requirements. And it can provide 256-bit security and achieve more than 200 gigabps with the performance. Next slide, please. So the design of the RockIS is based on the sponge construction and takes 256-bit key and generate 256-bit tag for the message authentication. And it supports three modes. One is the authenticated encryption with associated data, AEAD, and encryption only mode and keystream generation mode. And for the security, we claim 256-bit security against key recovery and forgery attacks in the non-respecting settings. And for the performance is one of the biggest advantage of the RockIS. And as far as we know, it is the first algorithm that exceeded 200 gigabps in the software environment. And in the encryption only mode, it can achieve 230 gigabps or the 0.122 cycles per byte. And in AEAD mode, it can achieve 205 gigabps. Next slide, please. So this is the detail of the algorithm and the round function of the RockIS. And as an internal state, it has 7 128-bit blocks and in parallel. And these 7 blocks are updated in the round function with the current state S and 2 input X0 and X1, and the new state S new will be generated. And the main operation in the run function is the AS run function, as the AS run function can be performed very well in the modern CPU thanks to the ASNI or the similar instruction set that is available on many modern CPUs. And next slide, please. And with that run function, the RockIS has 4 phases: initialization and processing associated data, encryption, and finalization. And in the initialization phase, internal state will be initialized with key, nonce, and constant, and apply run function 16 times. And after the 16 rounds of the initialization, key will be feed forwarded into the internal state again. And for if there is any associated data, the associated data will be processed, and then the message will be encrypted in the encryption phase. And after the encryption phase, key is again feed forwarded into the internal state and apply 16 times of the round function to generate a tag for the message authentication. Next slide, please. So the RockIS support 3 modes. The first one is AEAD. And in AEAD mode, the encryption and message authentication can be provided at the same time for the plaintext and associated data. And in the second mode is the encryption only mode. In the encryption only mode, messages input into the internal state of the algorithm. So the decryption will fail if there is any error in the ciphertext. And the last mode is the key stream generation mode. And unlike the encryption only mode, there will be no message into the internal state. So even if there is an error in the ciphertext, plaintext can be recovered except of course, these bits with errors. Next slide, please. So for the security, we claim 256-bit security against key recovery attacks and forgery attacks in the non-respecting settings. And the bottom half shows the brief summary of the security variation. The first one is the lower bound of the number of active best boxes in the initialization phase. And in order to provide 256-bit security, we need at least 43 active best boxes. And as this table shows, after 5 rounds, the number of active best box is exceed 43, and actually 68 is the number of the active best box. And so there is enough number of the active best boxes to offer 256-bit security. And also there is 16 rounds in total. So there are pretty much the security margin for against the key recovery attacks. And the second one is the security variation against the forgery. And also we need at least 43 active best boxes. And we confirm that we have 46 active S boxes for the forgery attacks as well. So 256-bit security can be provided. Next slide, please. So this is the result of the performance evaluation in AEAD mode. And we use the OpenSSL speed command to evaluate the speed and on the Intel Core i9-12900K and compare the performance with AES. And the graph shows the throughput when we changed the message size from 16 kilobyte to 1024 bytes. And when the message size is 16 kilobytes, the locus performs 205 gigabits, while AES is around 60. So more than 3 times faster than the AES in ZCM mode. Okay, next slide, please. So this is the conclusion. So I present the encryption algorithm ROCK-S. It can provide 256-bit security against key recovery and forgery attacks, and can perform very well on modern PC and exceed 200 gigabps, and support 3 mode, AAD, encryption only, and keystream generation. And we do not claim any intellectual property rights and no restrictions to use, and hoping that this algorithm can be adopted in many environments. And also we are planning to provide the implementation of the algorithm for OpenSSL and GitHub. And yes, that's all. Thank you very much.
Thank you very much. Any questions? Benson?
Thank you very much for the nice presentation. Were the tests on a single core, or did they use multiple cores on the Intel processor?
Sorry, I cannot hear you very well. Did you say, did I use multi-core in the evaluation?
The speed tests, I guess, did they use a single core or did they use multiple cores?
I only used the single core.
Okay, what was the cause of the, I guess, what's the limiting factor, performance limiting factor?
Sorry, could you say again?
Why does the performance stop at 200 gigabytes per second? What's the limitation?
Implementation?
Limitation.
Limitation.
Limitation in terms of?
Is it like the network card processing throughput on the core?
So I use the OpenSSL speed command, and the 16 bytes of the data is encrypted in 3 seconds, and calculate how many bytes are encrypted in the 3 seconds, and dividing by 3, we get the how many gigabits are processed during 1 second.
Okay, thank you.
Okay, thank you.
David?
Yeah, I had a quick question on the security you claim. This seems to be based on AES, and I was wondering whether there are security proofs that show that if you can break this, then you can also break AES, or is such work not done yet?
So the securities, so we use the differential probability of the AES S-box. So if you can break the AES, then that will affect the security of the RockIS as well.
Yeah, okay, but I meant the other way around. Suppose you have an attack on RockIS, do you also then automatically have an attack on AES, or are there attack routes that could
yes,
potentially avoid
I
that?
think the analysis of RockIS in some level can be applied to the analysis of AES, because we share the same round function. So if that analysis against RockIS uses the analysis of the AES round function, then affect the analysis of the AES as well.
Okay, thank you.
Yeah, thank you.
Right. All right. Thank you very much.
Okay, thank you very much.
Yeah, Scott. Okay. You want me to draw slides as well? Yeah.
Yes, thank you. These are a few brief comments based on a new draft we have implementing, showing how to implement ntrue. Now, the obvious question is why? We already have a post-quantum key exchange. Why do we need a second one? The reason is that Kyber has some plausible patent claims, and while NIST is actually working with the patent holders, they have not disclosed the agreements, and so we do not know if they will be acceptable to everybody. And this draft is here just in case. There are some people, say like the Free Software Foundation or maybe Cisco, which can't. Next slide. And why is it ntrue as opposed to like Bike or HQC? Well, ntrue is believed to be secure as Kyber. NIST admits that. NIST actually lists ntrue as a backup plan just in case it cannot get its agreements in time. And it performs fairly well. It's not quite as good as Kyber in terms of key generation, but still it's not that bad. And since it's you have CCA security, if you had to, you could actually use a single key exchange, key generation for mobile key exchanges, so it's tolerable. And also, best thing is it's known to be patent free because all the ntrue patents have expired, and that is and of the post quantum algorithms, only that ntrue and Michaelis has that property, and Michaelis is not usable. Okay. Now, the goals of the draft is to define what ntrue is. We have to do it more thoroughly than, say, the Kyber draft does because we can't rely on NIST to do the heavy lifting for us. NIST is not going to come up with some nice definition of it, and it's certainly not going to produce these test vectors, so we're going to have to do all that work. We're also following the ntrue round 3 submission, because that's the latest and that's probably going to be the last one. The other goal is to explain things in a way which is accessible to engineers. The round 3 submission has this nice description, but it's targeted towards mathematicians and cryptographers. you put that in front of a security engineer, and they're not going to understand it. And the other goal is to facilitate interoperable implementations and eventually how to use it within protocols. Now, one last slide. The questions I have for the research group. Do you agree with this general approach? Until we see the licensing agreements, it's just saying Kyber's solution is not enough. Now, my hope is that those agreements be perfectly acceptable to everybody, and this draft can just die. We can't depend on it that much. If does people have any questions about any issues with what's in the draft? Do they find things which are missing? Obviously, we need test vectors. What else? Thank you. Any questions?
All right, go ahead. Yeah, go on.
I'm Quindang at NIST. I don't have a comment, but I have something to share. Our agreements with the 2 patent holders have been signed, and we are in the process of getting approval to release detail to the public. And we strongly expect it to happen this month. And I'm not allowed to talk about the details right now, but all that I have known, it looks pretty good.
Yeah, until we see the agreements and put them in front of lawyers, I see this work is still necessary.
Yeah. Right.
Yeah, Scott, thanks for suggesting this at 114 here. And then, following through obviously pretty rapidly on this, so really appreciate the work on that. I guess the question I would have is, even if we see something aside from the patent thing that may collide, as much as I'm with you, and you despite having put work into it, just want to see it die. Should we keep it around in the event that we do find a later issue with, other approaches from a chem standpoint?
Yeah, I don't see this as a great amount of crypto diversity from Kyber, simply because they're both based on ideal lattices. And if we see a problem with the strength of ideal lattices, it will more than likely affect both. And so we'd probably need to go something like Bike or HQC at that point. It could be that they just found a problem with the Kyber infrastructure without affecting Entru. I would not bet on that.
Okay, cool. And then just to clarify possibly a bit, you obviously made the comment around Mechalase not being feasible. Do you care to expound on that a little bit?
Oh, it's yeah, because it's just a huge public key size. Everything else on Mechalase is wonderful. Just that a megabyte key size won't actually fit in the TLS key exchange.
Right. So yeah, just from one of the chairs, I suppose we'll wait and see.
Mm-hmm.
If you're happy to keep the draft alive, until we there's other information about whether and then we can decide then.
Okay.
Thank you. Right, so we are at the end of our agenda. Any other business that people would like to bring to CFRG at this time? Okay. Going once, going twice. Well, thank you for coming to CFRG, and enjoy the rest of your week at IETF.
Thank you. Goodbye.
This idea.